Okay. Hello, everyone. I hope you're all well. Before we start, I wanted to say a few words about the final exam. So the exam will be held during the regularly scheduled time, which will be May 11th, starting at 11:30. And you'll have a full 3 hours. That'll be much more than you'll actually need. I expect you'll probably need about half of that time, really. And just like exam 2, we'll use the B course's quiz function, and the questions will be true, false, multiple choice, and essay questions. It'll be open book, open notes, and remember, you're not supposed to have assistance from anyone else, and you're all bound by the honor code. And if you do have any issues or concerns about the final, please contact me or Alex. Once again, the exam will really focus on material that we went through in lecture. So your best studying resource will be making sure that you understand your lecture material. And on Thursday, Maria and Alex will give a review session to help get you ready for the exam. So any questions on the exam before we start? If so, go ahead and speak up. Okay. If not, I want to introduce Dr. Ben Snyder. Today's lecture is going to be on zeolites, and he's an expert on zeolites and particularly on transition metals within zeolites.
Okay, I guess I'll...
Ben, are you able to take over, share screen?
Yeah, I think you need to unshare your screen, or can I kick you off?
Unfortunately, it's not letting me do that. Maria, do you have control?
I think I have control, actually.
Okay, great.
Okay, that seems to have worked. 1 second here. All right, can you see that fine?
Looks good.
Okay, perfect. I'll get started. Hi, everybody. I'm Ben Snyder. You can call me Ben if you have any questions. Please feel free to just speak up. I won't be able to see if you're raising your hand via Zoom, so just jump in. I wanted to get started by first telling you guys a little bit about myself and what I'm interested in with chemistry. So when I was your age, I was just finishing up my undergrad degrees at the University of Rochester, in Rochester, New York, where I studied math and chemistry. This is back around 2011 or 2012, so a minute ago at this point. And what really kind of turned me towards chemistry as opposed to math were a few of the research experiences I had at the University of Rochester, working first of all for Professor Cara Bren, where I spent a lot of time using NMR spectroscopy to study electron transfer proteins called cytochrome C. And we were interested to use NMR to understand how the protein fold around the heme cofactor in these enzymes affected their electron transfer kinetics. And then I also worked with Professor Mike Neidig doing a very different kind of inorganic chemistry. In this case, we were interested in using spectroscopy to identify and characterize catalytic intermediates in carbon-carbon cross-coupling catalyzed by iron catalysts. And kind of collectively, what I learned from these experiences was that I was really interested in the intersection of inorganic and physical chemistry, particularly the idea that you could use rigorous spectroscopy to understand the geometric and electronic structure of inorganic molecules and how those correlate to their function. So based on that interest and some advice from my professors, I decided to pursue my PhD at Stanford with Ed Solomon, who's a world expert in inorganic spectroscopy. And this is where my interest in zeolites came from. So we were interested to see if we could take rigorous spectroscopic methods from inorganic chemistry and apply them to transition metal active sites in zeolites, which is something that people hadn't really done before. And I'll touch on a bit of what we accomplished towards the end of this talk. And then finally, after I finished my PhD in 2018, I was interested to see if I could take some of the design principles or insight that I got from my PhD and translate that into new materials. So this is why I came to work for Professor Long, to see if I could translate some of the things I learned from my PhD into a new class of materials called metal organic frameworks, which you may or may not have heard about at this point. But in today's talk, I'm going to focus on zeolites, and I'll divide the talk into 3 parts. And the first part, we'll talk about zeolite lattices. So this will mostly focus on the structure of zeolites and a little bit about their synthesis. In the second part of the talk, and third part of the talk, we'll move into some of the applications of these materials. So in the second part, we'll talk about zeolites as acid catalysts. And the third part, we'll focus more on zeolite chemistry from my PhD research, mostly which is involved in the understanding how you can use these materials to convert methane into methane. So zeolites are polymorphs of SiO2, and on this slide, I have 2 polymorphs of SiO2 that you might already be familiar with. So these are materials that have the same atomic composition, but different long-range order. So on the left, you have quartz, and on the right, you have glass. And you can kind of intuit by looking at the different structures of these materials, quartz being crystalline and glass being amorphous, that there's going to be some difference in their molecular atomic level structure. And if you zoom into their atomic level structure, you can see that this is in fact the case. So what I'm showing right here are just 2-dimensional slices of these 3-dimensional structures. And you can see that the atomic composition of these materials is the same, and the short-range connectivity of the atoms in these materials are the same. By that I mean each oxygen atom in white is connected to 2 silicon atoms in black, and each silicon atom in black is connected to 4 oxygen atoms. The 4th one is just missing because some atoms are omitted from this view for clarity. But you can see there's a big difference in the long-range order of these materials, the quartz being crystalline and glass being amorphous or disordered via the molecular level scale. So zeolites are also polymorphs of SiO2. They're a very broad family of these materials. There are about 230 different types. Some of them are naturally occurring and some of them are man-made. In this slide, I have 2 examples of naturally occurring zeolite minerals. On the left, chabazite, and right, wardnite. And again, you can maybe intuit based on the differences in the global structures of these materials. So chabazite having these nice cubic crystals and wardnite having these needle-like crystals. But there's going to be some difference in their molecular atomic level structure. And again, if you zoom in, you can see that this is the case. So again, we're looking at a 2-dimensional slice of these 3D materials. And in this view, you can see the kind of defining structural characteristic of zeolites. And that's that these materials have micropores, which give them a huge internal surface area. So these materials actually have a lot of void space in their crystal structure. So you can think of them almost as being spongy or porous. And these micropores are large enough to accommodate the passage of small substrate molecules up to as large as benzene. To give you an idea of the dimensions of these micropores, they can be up to about a nanometer diameter. So these micropores and the large internal surface area that they engender gives zeolites a lot of interesting applications I'll get into. But from the standpoint of coordination chemistry, what I think makes these materials really interesting is that you can take some of the silicon 4 tetrahedral sites or T sites and isomorphously substitute them for aluminum 3. And this creates regions of localized negative charge within the zeolite lattice. And these localized anions can be used to stabilize transition metal sites. So from the standpoint of inorganic chemistry, you can actually think of these materials as serving as extended ligands to metal ions. in terms of how we think about the global structure of zeolite lattices, there are a few ways you can kind of break this down. One of them is to think of their structures as cages connected by channels or pores. And in this slide, I have shown the structures of 3 different zeolites. I'll note that each zeolite is associated with a 3-letter code. There's nothing that's too systematic about that. It's usually just a shortening of the name. So the top row, we have the structure of morganite. The middle row, we have the structure of ferrite. And in the bottom row, we have the structure of the Linde type A zeolite. And what I've shown in the left column are the structures of these materials. And then in the middle column, overlaid is kind of a schematic representation of their pore networks. And then in the right column is a schematic representation of where the cages in these materials lie. So based on this way of thinking about the structure, you can classify zeolites based on the dimensionality of their pore networks. So for example, morganite we call a one-dimensional zeolite because it has an array of pores that have one dimension, which would be running into and out of the screen. Ferrite is 2-dimensional. You can see you have pores that run in and out of the screen as well as up and down the screen. And then finally, you can see that the Linde type A zeolite has a 3-dimensional pore network. So this is how we think about kind of global structure of zeolites. Moving to a more local picture, what I have shown in this slide are the different types of ring structures that you can find in the zeolites. So in the 10-membered ring that I've shown, I call this a 10-membered ring because it's a ring composed of 10 T sites. Some of the atoms in the T sites have been omitted here, but you can see that this is a ring of 10 of these silicon T sites. And you can have large rings, which would be like 12-membered ring, a 10-membered ring, or 8-membered ring, and these often define the circumference of a pore. And for these larger rings, you can actually bind metal ions into the walls of these pores. You can also have smaller rings, like 6-membered rings and 5-membered rings. And these often line the walls of the larger pores. And while these aren't really large enough to allow the passage of substrate molecules, they're small enough that they can bind metal ions to form what's essentially like a macrocyclic ligand. So the 6-membered ring here, in principle, could serve as a macrocyclic ligand to a metal site. And I want to emphasize here that there's a huge amount of structural variety in terms of each of these rings, which is going to depend on the lattice that you're looking at. So what I've shown at the bottom of the slide here are 3 different examples of 6-membered rings in different zeolite lattices, just to highlight the fact that these 6-membered rings can have slightly different geometric structures. So finally, how do you get these lattices? So the way these materials are synthesized is what's known as a hydrothermal synthesis. And what I have shown in this slide is a cutaway of a PAR bomb. So this is a high pressure reactor. And to make these materials, essentially what you do is you add silica, alumina, water, and some mineralizing agent, often a metal hydroxide or metal chloride species. And you heat these up sometimes as hot as 300 C inside of this PAR bomb reactor. So under the influence of very, very high temperatures and pressures, these materials will spontaneously crystallize out of solution. Now, because zeolites have this large amount of internal pore volume, their density is less than quartz. And because of that, they're less thermodynamically stable than quartz, which means that these synthetic conditions typically have to be under some sort of kinetic control in order to get these thermodynamically less stable polymorphs of SiO2. And one of the ways that this is accomplished is by adding organic molecules known as structured directing agents to the synthesis gel inside the PAR bomb. And what this does is it creates a kind of organic scaffold around which the zeolite lattice will self-assemble. And that's how you can get these really elaborate, complicated core architectures inside of these materials. So to get a better handle on this yourselves, what I'd like each of you to do now is to follow along with me here. I'd like you to open up your web browser and go to the website that's listed at the bottom of the page here. This is part of the International Zeolite Association Structure Database, which is a resource that anybody who does zeolite chemistry finds themselves using quite a bit. And this catalogs the structures of all the different zeolite lattices that have been identified thus far. So what I'd like you to do is I'd like you to open that website, and when you get to the website, click on the All Codes link that I've highlighted in the black box at the upper left of the screen. So I'll give you a few seconds to get that open. Okay, so hopefully you've got that open now. If any of you are lagging behind, just tell me to stop and I can slow it down. So if you clicked on the All Codes button, you'll be taken to this screen here, which has the 3-letter codes of all the different types of zeolite lattices. And I'd like you to click on MLR, which is Morganite. And that should take you to this screen here. And this screen is giving you a bunch of structural information about the Morganite lattice. So at the upper left, you see some of its crystallographic parameters, its unit cell parameters. It gives you some information about the different types of rings in the structure. So you can see that Morganite contains 12, 8, 5, and 4-membered rings. And you can also get some information about the size of molecules that can diffuse freely within the Morganite framework. So you might recall that I said Morganite is a one-dimensional zeolite, and you can see that's mostly because you only have free diffusion of something with molecular dimensions along the z-axis. So next, I'd like you to go up to the top of the screen, click on the 3D drawing drop-down menu, and go to the Morganite framework option. And that should take you to a screen that looks something like this. And this is just a way for you to kind of have a look at the three-dimensional structure of this zeolite. So the screen to the left, you should be able to click and drag this around to rotate the structure in 3D space to change your view of the structure. And then you can change the how the structure is displayed by clicking on any of these options under silicon and oxygen under framework display. And that's going to show you, that's going to display all of the atoms in the framework, not just the silicon. And then finally, if you want, you can look under surface displays, and this gives you the option to look at the van der Waals surface of the zeolite, which gives you a picture of where the void spaces are. So what I'd like you to do now is just take a couple of minutes to go back the screen that displayed all of the different 3-letter codes for zeolite. Choose one at random, whichever sounds appealing to you, and go through and use use this website to understand where the different types of rings are in its 3-dimensional framework, and see if you can understand what the dimensionality of the core network is for the choice that you've given. And so yeah, so look at the types of rings that are present, see if you can identify the different rings, and also the dimensionality of the core network. And just to remind you, you're going to go under 3D drawing and look at the framework there. So just take a couple minutes to do that. If you have any questions in the meantime, please speak up.
I've got a question about the synthesis. Do you find oftentimes that there are a lot of different types of like how pure can you get a specific zeolite in synthesis?
Yeah, so that's a good question. I personally am not sure of that because all of the zeolite synthesis was taken care of by collaborators during my PhD. So I actually never got my hands dirty with zeolite synthesis. I was only working with the spectroscopy. I think in principle, there are probably some similarities between zeolite synthesis and MOF synthesis where you get issues with phase impurity. So I do know that the reaction conditions have to be chosen very, very specifically. And I do know that the syntheses of these materials tend to be very, very sensitive. So it seems very likely to me that that's a problem that you would run into with these materials. Okay, do people need another minute or two, or are we good to move on? If I don't hear anything, I'll just keep moving. Okay, so now we're ready to move into the second part of the talk. So now that we understand something about the structure of these materials, we can start thinking about their applications. So in this second part of the talk, I'm going to focus on transformations involving hydrocarbons. But first, I want to convince you that zeolites are much more than just academic curiosities. So these materials are actually all around you in your day-to-day lives. Their most significant application in terms of what takes the most amount of zeolites on a per ton basis each year is actually in detergent. And in detergent, they serve to soak up metal ions from your laundry solution that would otherwise accumulate on your clothes as mineral deposits, things like ring around the collar. A lot of kitty litter is also made out of zeolites, and in this case, this application again relies on the ability of zeolites to soak up large amounts of fluids just based on their large internal surface areas. As kind of an aside, these materials also had applications in remediation of nuclear waste. So back in when the Fukushima disaster happened in Japan, the aid workers actually poured huge volumes of zeolite-based kitty litter into the cooling pools for the failed reactors. And in this case, the zeolites served to soak up radioactive iodine and cesium that were produced during the meltdown. And these harmful species were essentially sequestered inside of the pores of the zeolites. And the workers then took the contaminated zeolite powder and melted it down. And what this did is it trapped these radioactive species inside of the material, which ultimately became glass once it was melted down. In this way, the waste could be disposed safely without worries about the radioactive elements leaching back out. zeolites also find important uses in gas separation. So for example, in the International Space Station, zeolites are part of the system that recycles and purifies the atmosphere there. And this application just is based off of the fact that you can perform what's essentially a chromatographic separation of gases using microporous materials like zeolites. And then finally, in the bottom right, probably the most important industrial application of zeolites is in petroleum refining. So every gallon of gasoline that you pump into your car has been through a zeolite catalyst bed. And this is the application that I'm going to be talking about in the rest of this section. So a major process in petroleum refining is known as hydrocarbon cracking. And these cracking reactions require the participation of acid sites in zeolites. So what is an acid site? You get an acid site in a zeolite when you take a silicon T site, which is a silicon 4 bound by 4 oxygen atoms, and you do an isomorphous substitution with aluminum 3. And this creates a region of localized negative charge, which is compensated for in the acid zeolite by a proton. And call this a Bronsted acid site now. And this proton is extremely acidic. And there are a couple of reasons for this. So first of all, if you consider the conjugate base, the negative charge on the conjugate base is delocalized over 4 oxos. And then finally, because these materials are solid and porous, you can actually perform reactions in the absence of solvent. So the reactions we're going to be considering are known as solid gas reactions. And this is important because you have no solvent in your system that would level the acidity of the proton. So for example, if you ran a reaction in a zeolite in aqueous solution, the most acidic species you could generate would be hydronium. In the absence of solvent, you actually are able to realize much greater levels of acidity, so you get something behaving more close to a naked proton. And as a result, these acid sites are many orders of magnitude stronger than things like sulfuric acid. So you can do some pretty wild chemistry that you might not be familiar with. So these protons are acidic enough that you can actually protonate carbon-hydrogen and carbon-carbon bonds, forming these alkyl carbonium-like species that are shown in the right of the slide. So this superacidity opens up a range of new mechanisms that you can't really do easily in solution-based chemistry. And this is a big advantage in these, actually a requirement for these hydrocarbon cracking reactions. So hydrocarbon cracking essentially is taking a large saturated hydrocarbon and breaking it apart into smaller pieces, some of which are going to be unsaturated. And the reason you'd be interested to do this is because unsaturated hydrocarbons are much more valuable from an economic standpoint because they can be functionalized. So these molecules are useful synthons in chemical industry. But in this particular reaction that I've shown, which is the cracking of isohexane to isobutene and ethane, this reaction is never going to occur spontaneously because you need to move protons across large distances in the substrate molecule for this to happen. But this reaction is facilitated by superacid catalysis. So in the first step of this reaction, you have this very acidic proton attacking the carbon-carbon bond in the substrate, forming this carbonium ion pair. And in a subsequent step, the carbon that's indicated with an arrow is going to rebound on the negatively charged oxygen, forming a grafted oxygen-carbon bond and releasing ethane. And then finally, in the last step of the reaction, the proton on the substrate is going to rebound on the aluminum T site, releasing isobutene. So in this case, the aluminum T site, you could think of served as a shuttle, allowing for protons to be removed and placed in precise positions on the substrate, enabling this reaction to occur. So these reaction mechanisms can also be very useful for aromatic substrates. And in this case, you can use acid catalysis to isomerize, for example, xylene isomers. So in this reaction scheme, you'll have the acidic proton protonating the electron-rich ipso position of the carbon indicated by the blue arrow. And then in this intermediate, you again have an ion pair between a carbocation and a negatively charged aluminum T site. This carbocation is going to be susceptible to a methyl shift. And then finally, the acid site will be returned to its original state by accepting the proton from the metacarbon. So in this way, the acid site can also facilitate the isomerization of aromatic substrates. So these concepts are kind of all brought together under what's known as shape selective catalysis, which is a very characteristic mode of reactivity of zeolites that people are very interested in. So as an example of this application, there's a lot of interest in getting paraxylene. So paraxylene is a very useful molecule in chemical industry, I gather. But the problem is that you get xylenes from petroleum sources, and in this case, the xylenes come in a mixture of ortho, meta, and para isomers. And you would essentially like a way to separate or enrich your mixture in the para isomer. So one thing you can do is you can do a chromatographic style separation of these isomers using a zeolite. The idea here is that the para xylene is the least sterically demanding of all of the xylenes. So if you flow this mixture through a zeolite lattice, the para isomer is going to move through the lattice more rapidly because it can get through the constricted spaces in the lattice more rapidly. And people have quantified this, and they find that the rate of diffusion for para isomers, the para isomer is typically up to 1,000-fold more rapid than that of the ortho isomer. So you can do a pretty efficient chromatographic style separation of these isomers using a reactor bed packed with zeolites. But it turns out you can actually do even better if you combine this with acid catalysis. The idea here is you'd like to still make use of the meta and ortho xylene. So you'd like to isomerize that to the para isomer. And what you can do is put this mixture through a zeolite that has Bronsted acid sites. And because the para isomer diffuses very rapidly through the lattice, it's not going to have very much contact time with these aluminum T sites. So the chance that the para isomer is isomerized is relatively low. However, the ortho isomer is going to diffuse very slowly through the lattice. Therefore, it has more time to interact with these aluminum T sites, meaning that it has a much higher probability of being isomerized to the more rapidly diffusing meta or para isomers. So this combination of shape selective diffusion with acid catalysis provides a mechanism to separate and enrich your input stream with the more valuable paraxylene isomer. So that these sort of reactions involving hydrocarbon isomerization are currently probably the most industrially significant applications of zeolites. Now, in my PhD, I was focused more on the idea that you could use a zeolite lattice as a ligand to transition metal ions, and in this way create transition metal sites that can serve as catalytic centers. So to give you a kind of taste for what I mean by this, you could envision a six-membered ring inside of a zeolite lattice that I've drawn schematically here in the upper left of the slide. And if that six-membered ring contains two aluminum T sites, it in principle could support binding of a divalent metal ion. And here I've shown a reaction whereby you could install a copper 2 ion in this ring simply through exchanging with the copper chloride. And in this case, the chloride ligands on the copper will serve to deprotonate the aluminum T sites, and then the copper 2 center is going to be very happy in this square planar ligand field of oxygen. So in this way, the zeolite lattice can serve as a macrocyclic ligand. And what's interesting about this is that the ligand fields provided by this ring is very weak. So you have a kind of interesting combination of a ligand that's very rigid, but also very weakly donating, which is very hard to accomplish in molecular chemistry. Usually weak field ligands, weak field macrocyclic ligands tend to be much more flexible. And the macrocyclic ligands that are rigid tend to be very strongly donating, things like hemes or porphyrins. In the second example here, you could envision binding also a metal ion in a ring that has much more shallow curvature. And in this case, the zeolite lattice can serve as a bi or tridentate ligand as opposed to a macrocyclic ligand. And one thing that's nice about zeolites is that these materials are incredibly robust. So you can subject them to very high temperatures, and they'll survive much more easily than organic molecules. So in this scheme, you could envision taking this copper 1 site that I've shown bound to the zeolite lattice, heating it up very hot to remove any of the bound solvent. And in this way, you can generate transition metal sites that have open coordination positions. And again, this is something that's kind of challenging to do in small molecule chemistry where there's solvent lying around. So you can generate these metal sites with open coordination positions that then can interact with substrate gases. So for example, in this case, you could flow CO over your zeolite, and this copper 1 site will be very happy to pick up CO ligands from the gas stream. So the characteristics of these ligands, of zeolite lattices as ligands, I would say are, you can have these weak field macrocyclic type situations. And another characteristic is that you can have metal sites with open coordination positions. So moving into a little bit finer detail, thinking about the zeolite lattice as a ligand, metal ions are going to invariably be bound through these lattice oxygens. And there are 2 types of lattice oxygen ligands that you're going to find in the zeolite lattice. You'll have oxygens that bridge aluminum and silicon, and these are going to carry some partial negative charge by virtue of being part of an aluminum T site. And these bridging oxygen atoms are going to have 2 lone pairs that can be donated into a metal ion. So you'll have an in-plane sp2 hybrid, which is nice and directional, and then you'll have an out-of-plane p orbital that can participate in pi bonding interaction. The second type of oxygen atom you can have is one that bridges between 2 silicon atoms, and this is going to be a neutral species, and as a result, it's not going to be as good of a donor. And I just want to point out I have some kind of subtle changes between the neutral and anionic cases. The neutral lone pairs, since they don't carry negative charge, are going to be slightly more stable and slightly more contracted. So these are more stable, and the orbitals are less diffuse, so they're going to be more weakly donating. But the zeolite lattice can also play an important role in determining how strongly or weakly these oxygen atoms donate into a bound metal center. So for example, if we look at this 6-membered ring that's in the beta type zeolite, this ring doesn't really have to distort much to accommodate a square planar metal ion. However, the Chabazite 6-membered ring, which has trigonal symmetry, needs to distort considerably to accommodate a square planar ion. And as a result, the metal ligand bonds in this lower structure are significantly strained. You can see that in their predicted metal ligand distance, which is elongated by about 0.1 angstroms. So in this case, strain from a zeolite lattice can play a pretty big role in determining how these oxygen atoms donate into a metal ion. So now, in my PhD, we were interested in understanding how we could use metal ions in important applications, and the application that we focused on was the conversion of methane to methanol. So the reason that you would want to convert methane into methanol is that methane is a gas, so it's very difficult to transport in useful quantities. So for this reason, you have to do things like build huge pipelines or transport the methane as liquefied natural gas, and these are both very energy-intensive options. And for this reason, a lot of methane is wasted. So on the right here, I've shown a picture of an oil rig, and it is burning the methane that's associated with the oil deposit because it's not economically feasible to recover the methane, and the resulting CO2 is a less harmful greenhouse gas than methane. So one way you could get around this problem, in principle, is by converting the gaseous methane into liquid methanol. So because it's a liquid, it'll be much easier to transport, and methanol is also a very useful fuel and synthon in the chemical industry. And this is actually already, this transformation of methane to methanol is already done on a pretty massive scale, worth many billions of dollars. And the way it's currently done is what's known as the syngas route. And this involves taking methane and water, heating them to very high temperatures and pressures. And under these conditions, you get what's known as a water-gas shift reaction. So this methane and water will go to CO and a mixture of CO and hydrogen. And then that mixture of CO and hydrogen can be subsequently transformed into methanol and hydrogen. So this syngas route requires some very, very forcing conditions to keep these reactions under thermodynamic control. And because of that, this reaction is very energy intensive, and it requires a huge capital investment, so you need a very large chemical plant for this to work. So this doesn't actually really get us a solution to the problem of recovering methane from remote locations like oil wells in the middle of the ocean. To do that, you'd like to create a route that's much less energy intensive, and people have envisioned a way towards this as what's known as a direct route. So in this sort of scheme, you take methane and an oxidant, ideally O2 from the atmosphere, and with some catalyst, that will directly form methanol in a single step. So in this sort of scheme, the challenge is no longer related to providing very high temperatures and pressures. So this is no longer an engineering challenge, but actually a chemical challenge where you're trying to stop the methanol from being over-oxidized to CO2, which is very favorable thermodynamically. So in this case, you need to develop some very clever chemistry to get around this problem of oxidizing methane to methanol selectively without over-oxidation to CO2. And the key chemical challenge in this is actually figuring out ways to cleave the very, very strong carbon-hydrogen bond of methane, which is one of the most inert bonds in chemistry. So it turns out that some synthetic systems have been identified that can perform this reaction, albeit not very well. And there's been a huge amount of interest in understanding the fundamental aspects of this reactivity so that maybe it can be modified and put into practical technology. So one of these systems that attracted a huge amount of attention were zeolites exchanged with iron. In this sort of scheme, you take your acid zeolite, you replace some of those Bronsted sites with iron, and in this case, you get a zeolite lattice that contains a sort of heterogeneous distribution of different types of iron sites, which I've shown schematically in the lower left of the slide. Now, when you take this iron exchange zeolite and you heat it under a reducing atmosphere, like helium, to very high temperature, you form a reduced iron 2 site, which was known colloquially as alpha iron. And this alpha iron site will react with N2O at 250 C to form a reactive oxidant known as alpha oxygen. And alpha oxygen will react with methane instantaneously at room temperature to form methanol. So it'll cleave one of the strongest, most inert bonds in chemistry at room temperature rapidly, making it one of the most reactive molecules that's ever been isolated. So this really captured the imagination of a lot of inorganic chemists. There's a lot of interest in understanding, what are the nature of these alpha iron and alpha oxygen sites inside of the zeolites, and what allows them to function in this remarkable way. But it turns out studying metal sites and zeolites is very challenging because you have this heterogeneous distribution of metal lands. And it ends up being very challenging to take these systems and study them spectroscopically and understand what spectroscopic signals are coming from your sites of interest versus these so-called spectator sites that don't contribute to reactivity. And because of these challenges, many of which went unrecognized, there's a huge amount of speculation over the nature of the alpha oxygen site, largely because there were no reliable experimental data that would have kind of provided insight into this species. So what follows, I'll kind of give you the answer first, and then some kind of post hoc explanation for how we came to that answer. So in my PhD, we figured out that that alpha iron, the reduced iron site, is a square planar species bound in a 6-numbered ring containing the particular configuration of aluminum that's shown in the figure. And as a very brief exercise, what I would like you to do is take the ligand field diagram that I've shown here and fill it in with the appropriate number of electrons for a high spin square planar iron 2 site, and then give some educated guesses on the orbitals that are associated with this ligand field diagram. So what's the energy ordering of the orbitals? So I'll give you a couple of minutes to think about this, and then I'll give you the answer briefly. Again, if you have any questions, please feel free to jump in. Okay, so we'll start from the top and go to the bottom. The top is probably the easiest one to have guessed. So at the top you have the x squared minus y squared orbital, which is going to be most destabilized just due to its direct interaction with the sp2 in-plane lone pairs. So you have a very strong sigma antibonding interaction there. And I should mention before that high spin iron 2 is a d6 ion. So your lowest occupied molecular orbital in this diagram is going to be doubly occupied. Moving down in energy, you have the d pi orbitals, which are going to have a pi antibonding interaction with the out-of-plane 2 orbitals. You have the xy orbital, which is non-bonding. And then finally, at the bottom, this is a little bit tricky, you have z squared. And the reason z squared is lowest in energy in this ligand field diagram is because it has the appropriate symmetry to engage in a configuration interaction with the 4s orbital, which isn't shown here. So in this configuration interaction, z squared is stabilized and the empty 4s is destabilized. And this is a characteristic of square planar ligand fields. So z squared is almost invariably going to be lowest in energy in a square planar site due to 4s mixing. Any questions before I move on? Okay, so the way we got to this answer very briefly is that you can you can look at the UV-Vis spectroscopy of these ion exchange zeolites, and by looking at how the UV-Vis spectra respond to different levels of iron loading, you can figure out which features in the UV-Vis spectrum correspond to spectator iron and which correspond to the active alpha iron site. And in this way, we correlated this UV-Vis feature at 15,900 wave numbers with the active alpha iron site. And so we have a UV-Vis feature, but we don't really know anything about the ground state from which it originates. So what you can do is you can do an experiment called magnetic circular dichroism, or MCD. And in this experiment, you see essentially the same spectroscopic features that you see in the UV-Vis spectrum. However, the intensity in MCD, the spectral intensity of each of these features, is going to reflect magnetic properties of the ground state from which it originates. And by that, what I mean is you can look at this feature in MCD spectroscopy from alpha iron. You can look at how its intensity changes with respect to the applied magnetic field and temperature. I just saw something pop up on my screen. Did I have a question?
Yeah, sorry, I'm a little bit confused on the filling of the orbitals. So why do we have unpaired why do we put the unpaired electron on the x square minus y square while the energy level is so high?
Sorry, I couldn't quite hear you there. Could you repeat that?
Oh, sure. So my question was that why don't we fill up the lower energy orbitals before putting the electron on the x square minus y square?
In what I was talking about previously, I was just moving from the top down in energy because the most destabilized orbitals are kind of easiest to assign. So it's not, I'm not making anything that breaks Hund's rule or anything like that. Like if you were popping electrons into this, you obviously would still fill the lowest energy orbitals first. I was just talking about the highest energy orbitals first because they were the ones that are easiest to assign, in my opinion, from the ligand field diagram. Does that answer your question?
Actually, sorry, no, I'm confused about like why don't we have paired electrons instead of?
Why don't you have paired electrons in what?
In the.
Then I think the question is, why is it high spin instead of low spin?
Yeah.
Okay,
yeah.
great.
Sorry. Yeah.
Great. So that's a very good question. And it turns out that if that equatorial interaction was just a bit stronger, so that the x squared minus y squared orbital was raised just a bit in energy, you would actually get to an intermediate spin or S(1) case. But it turns out that in this particular ligand field, you're kind of right on the borderline where the ligand field is strong enough that you get this very big anisotropy, equatorial axial anisotropy, but not strong enough to destabilize x squared minus y squared so that it would become low spin.
Oh, I see. Thank you.
Does that answer your question?
Yes, thank you.
Okay, great. So moving back to MCD, again, by looking at the response of this MCD feature of alpha iron, how it changes with respect to magnetic field and temperature, we were able to understand the nuclearity and spin of this species based on its magnetic properties. And we found that it was a mononuclear SF2 site based on this. And basically, in order for a mononuclear SF2 iron 2 site to have a ligand field transition at this high of energy, that basically very strongly pointed us towards looking at a square planar site, because one characteristic of a square planar site is that it's going to have this relatively high energy ligand field transition. So now what we're going to do is we're going to take alpha iron and we're going to transfer an oxygen atom from N2O into this vacant axial position to form alpha oxygen. So again, I'm kind of giving you the answer, but a big deal for my PhD research was actually understanding the structure of this alpha oxygen site. And what we found was that this was an iron 4 oxo site with an axial oxo ligand, the iron oxo interaction being very, very strong. And this type of intermediate is also used in biology for oxidation reactions. So for example, in cytochrome P450, you can again look at a ligand field diagram here And this is going to be an S(2) iron 4 oxide site. Again, this is going to be high spin because the zeolite lattice is a pretty weak field donor. And the important thing that I want to point out here is that you have a vacant Z² orbital. And this is going to serve as the reactive frontier molecular orbital and the reaction of this site with methane. And how are we, Maria, how are we doing for time, by the way? Do I have until 10:40?
You've actually got until 11 if you need it.
Okay, that's great. I will slow down a little bit then. Okay. So this alpha oxygen site has a vacant Z² derived molecular orbital that's going to serve as the reaction channel for the activation of methane. And here in this slide, we're going to focus on what allows this site to cleave the very strong CH bond of methane. And the way I would think about this is that you're going to have a donor-acceptor interaction between the filled sigma bonding orbital of the CH bond and the vacant iron oxo sigma star orbital. So what happens is, as you move from the ground state, which is labeled 1 in this scheme, in the transition state, which is labeled 2, what's going to happen is the CH bond and the iron O bond are each going to elongate. And as the iron O bond elongates, that frontier molecular orbital is going to be stabilized, so it's going to be lower in energy. And as the CH bond elongates, the CH sigma bonding orbital is going to be destabilized. So these structural changes bring the CH sigma bond and the iron O sigma star levels to closer in energy. And then at the transition state, you have very nice energy match and orbital overlap between the CH sigma bond and the iron O sigma star level. And this allows a nice covalent delocalization of the iron-centered hole onto the carbon. So in the transition state, essentially what you have is a nascent methyl radical. And you have the CH bond that's half broken and the OH bond that's half formed. And finally, as you move past the transition state, the hydrogen atom is fully transferred onto the oxygen atom, and the hole localizes on the methyl. So you're left with a methyl radical that's loosely bound to this active site. And finally, in the subsequent step, moving from 3 to 4, the methyl radical will rebound on the oxygen, forming a carbon-oxygen bond. So in steps 1, 2, and 3, you ultimately have the CH bond transferring a proton and an electron into the iron site. So you reduce the iron by 1 electron. And a subsequent step with CO bond formation, you further reduce the iron to its iron 2 state, which returns it to its the reduced state of the active site. So the reason that this reaction works for this particular active site comes down a lot to the strength of that OH bond, the OH bond of the ferric hydroxide species that you form. And this is because for this reaction to have a driving force, the strength of the OH bonds that you form needs to be comparable to the strength of the CH bond that you break. So you've broken a very strong CH bond at 104 kcals per mole. So for this reaction to have a driving force, you need to form an OH bond that is also very strong, on the order of 104 kcals per mole. And for an iron 3 hydroxide site, 104 kcals per mole is much stronger than what's typical. So an iron 3 hydroxide site will typically have an OH bond strength on the order of 70 to 90 kcals per mole. So there's something unusual about the properties of this alpha oxygen site that allows it to form this incredibly strong OH bond. And when you're thinking about an OH bond being formed, you can parse this into 2 contributions. So you're transferring an H atom to this active site, right? And the H atom is made up of a proton and an electron. So the OH bond strength then can be decomposed into a reduction potential of the iron 4 site, followed by protonation of the resulting iron 3 site. And these are quantified as a reduction potential of the iron 4 site and then the pKa of the resulting iron 3 oxide that you form. And it turns out what's important in this case is that the interaction between the iron 4 site and its axial oxo ligands, so moving back again to species 1 in the scheme, the interaction between the iron 4 and the oxo is extremely covalent. And it turns out that as you increase iron-oxygen covalency, the reduction of the iron 4 site becomes much more favorable. However, the pKa trends in the opposite direction. So with increasing iron O covalency, you have less negative charge localized on your oxo, which makes it less happy to accept the proton. So in this case, it turns out that the reduction potential contribution dominates, and that's what's responsible for this iron-oxygen bond being incredibly strong. This active site has a very unusually covalent iron-oxo bond, resulting in a large reduction potential. So to kind of get a sense for why that might be the case, we can look at a kind of cartoon MO diagram. And what we found here is that the zeolite lattice takes a really interesting role in actively creating a very strong iron 4 oxo interaction. So in the left-hand side of this figure, I've shown a qualitative MO diagram of this SF2 iron oxo site. And in this case, the zeolite lattice is rigid and kind of locks the active site in the geometry that's shown, where you have an equatorial ligand field from the zeolite lattice and then an axial oxygen ligand. Now, if you were binding this active site to a floppier ligand so that it could distort, what actually would happen is one of these equatorial L ligands would shift, and it would shift to occupy the coordination position trans to the oxo ligand. So in this case, the zeolite lattice holds the iron oxo core in an inherently unfavorable geometry. And the reason this geometry is unfavorable is that if you focus on the occupied x squared minus y squared orbital, this has a sigma antibonding interaction with the equatorial ligands. And this destabilizing sigma antibonding interaction can be partially relieved by shifting that ligand to the vacant transaxial position. So what this does is it stabilizes that electron in x squared minus y squared at the expense of destabilizing the vacant z squared molecular orbital. So the site in that case is more stable, but it's also less reactive because you've raised the energy of this z squared molecular orbital, and that's going to negatively affect its energy match and orbital overlap with the CH bond of methane. So the idea here is that the zeolite lattice actively holds this iron oxo core in a configuration that engenders very high iron oxo covalency and high reactivity. So if that was all a little bit too detail oriented, I know some of these things you kind of have to spend some time with to wrap your head around. But there's an essentially equivalent, maybe less detail oriented explanation of this effect. So hopefully this might make a bit more sense if you're confused. One way you can think about this is if you look at a high spin iron 4 oxo and its reaction with methane to form a high spin iron 3 hydroxide product, you see that there's a difference in the stable geometry of the iron oxo and iron hydroxide. So in this case, what the zeolite lattice does is it's going to distort the iron oxo core into a geometry that more closely resembles that of the high spin iron 3 hydroxide product. And in this case, the zeolite lattice is going to provide about 5 kcals per mole of distortion energy to bring the geometry of the reactant closer to that of the product. And this also significantly reduces the barrier for H atom transfer. So you could think of this so-called emphatic effect or rigid constraint from the zeolite lattice is kind of spring-loading the active site for reactivity. So now I just want to invite some audience participation here. If I recall correctly, you might have spent some time thinking about P450. Is that right, Jeff?
Yeah, we did.
Okay. So I would invite us to think a little bit about the different strategies that these iron oxo sites use to achieve high reactivity. So I'll just recap a little bit about what we've said about alpha oxygen here. In this case, we're going to think about how the ligands tune the reduction potential and pKa's of these iron oxo sites. And what I've told you is that the weak donation of the zeolite lattice into this iron oxo core of alpha oxygen results in a high spin electronic structure, and this leads to a very favorable reduction potential, which facilitates H atom abstraction from hydrocarbon substrates. So in this case, the favorable reduction potential of the iron oxo core drives reactivity. Do any of you have any thoughts about P450 compound 1, which is an S1 iron 4 oxo with a porphyrin radical? How do you think this very different macrocyclic ligand, how do you think this tunes the reactivity of the iron oxo core? Do you have any thoughts here? This is kind of tricky, so if it doesn't immediately jump to you, really don't worry about it. So does anybody have any thoughts in one direction or another?
Would that make it so that the highest unoccupied state is not, in fact, the iron oxo, and it'll be less reactive? There will be other occupied states that it might try to go towards.
So that wasn't the direction I was quite thinking in. What I might think about is so the zeolite lattice is a very weak donor, whereas the porphyrin and this axial thiolate are relatively speaking a much stronger ligand field, and you can see that from the fact that the iron oxo core in this case is an S1 species as opposed to S2. So do you have any thoughts as to how strong donation of these other ligands into the iron is going to affect for example, the pKa of the oxygen ligand? So I'll give the answer here. So in this case, the covalency of the iron oxo bond is going to depend a lot on how strongly donating the other ligands are. So if the other ligands donate weakly, then the oxo is going to donate very strongly to compensate. And therefore, it's not going to have a very favorable pKa. So in this case, you've got strong donation from a thiolate and an equatorial porphyrin ligand. And these make the iron center relatively electron rich, which means that the oxo is not going to donate its electron density as strongly into the iron center. So more of the negative charge of the oxo is going to remain on the oxygen ligand and not donate into the iron. So that oxo is going to be more basic, giving it a more favorable pK. So the tricky thing about this active site is you have to think about where the electron and the proton go. Whereas in alpha oxygen, the electron and the proton both went onto the terminal oxygen ligand. In P450 compound 1, you have this radical on the porphyrin ring, and it's actually that's where the electron that you put into the system is going to go. The electron is going to go into the porphyrin ring and not the iron oxo. So in this way, nature kind of cheats. So it gets a favorable reduction potential based on the favorable reduction of the porphyrin radical. And then it's able to have a favorable pKa through strong donation of these ligands into the iron center. So in this case, nature has kind of divided the problem up into two pieces and solved each of them independently, which I always thought was a very acute solution to this problem. Any questions about that before I move on? Okay, there are no questions. So in the talk today, I just wanted to briefly summarize what we've been over. So the first part of the talk, we talked a bit about the structure of zeolite lattices and their microporous nature. And in the second and third parts of the talk, we focused a little bit about how the microporous nature of these zeolites and their acid sites give many important applications. So the acid sites can be used for hydrocarbon cracking, or alternatively, we found in the third part of the talk that the acid sites can serve as points of exchange for metal ions, and these metal ions can serve as catalytic centers to perform some very challenging chemistry that, again, is not easily done in solution phase or with small molecules. So I guess I have until 11 o'clock. So what I wanted to leave us on then was just another quick exercise for everybody. So what I would like you to think about briefly is I've shown this hypothetical copper-1 site down to a zeolite lattice. And what I'd like us to do is just draw a qualitative MO diagram for this linear copper-1 site. So in this case, what we can assume is all of the atoms lie in the same plane. And just remember that each of these oxygen atoms has two donor orbitals that can participate in bonding with the copper-1. So you're going to need to remember how many d electrons copper-1 has, and what are the empty orbitals on copper-1 that can accept electrons as even ligands. And then finally, if we have a bit of additional time, you might think about what happens if you twist one of the ligand planes by 90 degrees. But for now, we'll just focus on the problem as stated. And in a few minutes, we can revisit. I'll show you the qualitative MO diagram that I've drawn, and we can compare it to whatever you have. Any questions about this little exercise before we get started?
So only consider the oxygen lone pairs as interacting with copper?
Yeah. So each oxygen, just to refresh your memory, each oxygen atom is going to have an in-plane sp2 donor, which can participate in sigma interactions, and then it's going to have an out-of-plane p pi orbital, so a p orbital that can participate in pi interactions. Okay, so in the interest of time, just click through here and walk you through the MO diagram that I wrote. Again, this is all qualitative, so don't take the energy splittings here too seriously. But hopefully the orderings that I've drawn you can agree with. So first, we of course want to understand what are the filled donor orbitals on the ligands, and what are the empty acceptor orbitals on the metal. So starting with the metal on the left, copper 1, should hopefully all know, is a D10 ion, which means that all of its d orbitals are filled. So these are not going to participate in bonding interactions with ligands that are sigma donor and pi donor. So if we had back donating, if we had ligands that could participate in back donating interactions, that would be a different story. But zeolite lattice drive ligands they're pure donor ligands. So the empty orbitals on the copper that are going to participate in bonding are going to be the 4p and the 4s. And then on the ligands, we have two in-plane, oops, my labels here are incorrect. So on the bottom, it should be sp2, and on the top, it should just be p. So sorry about that confusion. So we have four donor orbitals, which are going to be the symmetric and anti-symmetric combinations of the sp2 orbitals, and then the symmetric and anti-symmetric combination of the p pi orbitals. And the sp2 orbitals are going to be slightly stabilized in energy because they have more s character. So in this case, now we can create bonding and anti-bonding combinations with these orbitals. And moving from the top down, we're going to first have the most destabilized orbital through direct sigma antibonding. So that's going to involve the sigma antibonding interaction between the 4p on the copper and then the in-plane sp2 hybrids of ligands. Next, you're going to have the antibonding pi combination, and then finally you're going to have one p orbital that is going to be the one of the in-plane p orbital on the copper that does not have any donor interactions. There are no donors on the ligands that have the appropriate symmetry to interact with this. And then finally, you'll have a weaker sigma antibonding interaction with the symmetric combination of the sp2 hybrids of ligands. And then the bonding orbitals, fulfill are basically analogous. So, does anybody have any questions about the orbitals that I've drawn? Everything is clear? All right, well, I'll take the silence as an affirmative there. So with that, I think that brings us to the end of today's content. So thank you all for your attention. Let me know if you have any questions overall about what you heard. And yeah, I'll hand it back over to you now, Jeff.
All right, great. Thank you very much, Ben. That was fantastic. Do we have a last question before we adjourn? Okay, if not, everybody, oops, here we go. Golsa, go ahead. Oh, Golsa says thank you. All right, everyone. So remember on Thursday, we'll have a review session, same at the usual time. So see everyone then. Thanks, Ben.